Now part 3, the central part of weeks 2 and 3. That is the most important part. Because as we said, given a model, you can do very simple linear classifier. That's so just a dot product. But the question is really how to learn that model W from data, which is a set of pairs instead of input-output pairs, right? That's the core of the perceptron learning algorithm, and that's Rosenblatt's invention. Now we'll do it assuming augmented space already, assuming that this space is already have this bias built as an implicit first dimension. And let's say we're doing spam filtering, and positive class is spam, and negative class is not spam. And we need to learn a linear classifier like one of these lines, right? Yeah, but how do we do that? Okay, so here's the very, very, very simple perceptron algorithm. It's just a few lines of code, right? Input D, output W, and initially you set W to 0 vector, that is 0 on every single dimension, and as long as the data set is not converged, that means as long as you still have mistakes on this data set, then you go through this data set again. So you cycle through this data set multiple times. Each time is called an iteration, or in some other literature it's also called an epoch. When you see epoch 7 or whatever, it means you're doing the 7th cycle over the data set, right? So for each iteration or each epoch, you go through each example, XY pair in this data set. And if your current model classified this example wrong, that means if this example should be positive, that is Y should be +1, and your dot product is negative, then you're misclassifying this example. Or in the other case, if your example is negative, that is Y is -1, and your current model says, okay, I'm positive dot product, then you're still doing wrong. So if you don't agree with the correct label Y, including the tie-breaking case, okay, because we don't want to be doing chance, right? So even if it's a tie-breaking case, we consider it wrong. You have to be positive to be correct. Anyways, if you're misclassifying this particular example XY, then we need to do an update or fix on that example. And the update is as simple as it could be. Just W plus equal Y times X. In other words, if it's a positive example, you just kind of add it to the current weight vector. If it's a negative example, you just subtract it from the weight vector. That's it. It's really, really by far the most simplest machine learning algorithm. Well, you want to say maybe nearest neighbor is probably the simplest machine learning algorithm. But, well, I kind of agree because there's no training time procedure, really, right? So training time procedure, you do nothing. Testing time, I'll look at what kind of examples are closest to you, right? But at testing time, you have some work. You have to measure the distance between your input example to every single of my training examples, and then sort and take the top k. Well, you probably don't need to sort, but you need to figure out the top k and then do a majority vote. So at testing time, you do actually a lot of work. Imagine you have 10 million data examples in your training data, and at testing time, you have to kind of measure the distance from the input test example with every single one of your 10 million training examples. That's a lot of work. So really, nearest neighbor is deferring all the work in training time to testing time. So that's actually not very good, not very nice algorithm, right? Perceptron, you do some work in training, some very simple work, but at testing time, you just do a dot product. That's it. So really, really simple, right? Yeah, keep cycling through and update if there's a mistake. If there's no mistake, then you don't update, right? Because if my weight vector correctly classifies this current example, that means I'm good. You're good, then you don't want to change it. As long as it's good, don't do anything on it, right? If it's bad, then do a simple update until all examples are correctly classified. Then that means you converge. If your data set is not separable, then you will not converge. But let's assume for now that the data set is perfectly separable, so that we'll prove in part 4 that this algorithm will eventually converge after a very small amount of mistakes or updates. Okay, so this is an update. So for example, W is pointing to this direction, and a positive example X is misclassified, right? So if W is pointing to this direction, that means this half of the space is considered positive by the current model. Now, this is an example that you would misclassify, right? So it's a positive example, and its dot product is negative, so you need to do an update. The update is W becomes, new W becomes W plus this X, right? And W prime is the new direction, right? Okay, let's look at an example later, but here's a side note on mathematical notations. In these slides, I'll try my best to be consistent in notations, and that's not an easy task, you will realize. So for example, I use boldface, lowercase for vectors, and italic for scalars, and matrix I use another font. And more importantly, I will try to simplify my notation as much as possible as long as it's consistent. In other words, I will avoid unnecessary superscripts and subscripts and all these kind of funny notations by using a Pythonic rather than C or Java style notational style. This is kind of a relatively new mathematical style because most textbooks and most papers do not use those styles. They're consistent. Most textbooks, at least, they're consistent. Papers, sometimes they're not consistent, but most textbooks are consistent, but kind of using overcomplicated notations. Let's compare this version from a textbook of Perceptron and this version from our slides. So on the left, we have good notations, consistent and Pythonic style. And this from a textbook is bad notation because it's inconsistent that, you know, both vectors and scalars are using the same font, same font. That's very confusing. Whether xi is a vector or not. Now xi, whether is it really the ith dimension of this vector x, or is it the ith vector, right? In this context, it really means the ith vector, not the ith dimension of a vector. But how do you tell? There's no hint in notation, right? And the other thing is there is an I here, so you're ranging over from I for I equals 1 to the size of data set. That's basically a C-style for loop. We want to write a Pythonic for loop that is for x, y in D. You know, if you write Python, you really write in these notations. You don't need to care about I. Okay, most of the time you don't need this loop variable, so that simplifies a lot of things, right? So for x, y in D, I don't care whether it's the 5th or 7th. Who would care about the loop variable, right? Because it plays no role in the learning algorithm. And the other thing is it has a explicit bias B, which we also know you have to update as well. So this is the version with Perceptron version with explicit bias. You see that there are two updates. One is on the weight vector, the other is on the B. Why don't you just merge them, like as what we did in the augmented space, right? So there are a lot of problems with a standard textbook notation. They're overcomplicated, and sometimes they're not very consistent, and they use, you know, superscripts and subscripts which are not necessary. They're just kind of inspired by the C or Java style of writing code, which is a bad style. You know, everything in this course needs to be written in Python. And Pythonic style is the most beautiful style in terms of programming languages, right? Okay, back to our Perceptron demo. So we talked about, you know, doing an update, and this is a misclassified example, positive example misclassified. You should add it to the current weight vector, and your next weight vector will become this one, right? And then you go to the next example, and positive example is too misclassified, right? Because it's, you know, kind of totally opposite direction. You add it to the current weight vector, and this is your next weight vector, W prime. Okay, this time everything is classified correctly. Then after this iteration, the perceptron will stop because it has converged. Okay, so yeah, perceptron will actually converge pretty fast, both in theory and in practice. So in the next part, we will prove it. Perceptron convergence theorem, that perceptron actually converges pretty fast.